Hi Lydia, just going to give you a bit of feedback on your assignment. So I'll go through slide by slide and just make some comments and hopefully you'll find those useful. Okay, this all looks absolutely brilliant. Just watch out for one tiny mistake, which is that one there. Obviously it's kilograms meters per second squared. Obviously you know that because you put it up in the table above. Yeah, this all looks absolutely brilliant. Have a quick look at what I put on the next slide. It's an example of something that I quite often use in the classroom you might find useful. So when I'm thinking about getting students to understand units, then this is an example I quite often use. So I look at this idea that work done equals force times distance, which obviously they've met at GCSE. I also get them to look at GPE equals MGH, again, something which they will have met at GCSE, and then the same for kinetic energy. So half mv squared, again, something they've met at GCSE. And then I find it quite useful to get them to think about the units for each of these. So if I look at the first one, these are all going to be measured in joules. They're all types of energy. But here I've got Newton meters, which as you shown over there in your previous slide is kilograms meters per second squared, and then multiplied by meters. So we end up with the unit kilograms meters squared per second squared. If I do the same thing down here, I've got MGH, so I've got kilograms. Obviously G is measured in meters per second squared, and then height is measured in meters, which means I end up with the same kilograms meters squared per second squared. And then finally, if I do exactly the same for kinetic energy, obviously half has no unit. So again, I've got mass, which is kilograms, and then I've got V squared, so meters squared per second squared. It's just a really nice way of showing that whichever way I look at it, I always end up with the same units for energy. So obviously this then is what we break down into joules. Yeah, again, this is lovely. I quite like the fact you've got some examples on the right hand side there, because obviously there are a few that have to learn at GCSE physics, so this is a really nice next step up. I've just put at the bottom of the yellow box an example of Cognito do a number of maths videos, and this one is one of 4 on standard forms. So sometimes I use this with students just to remind them about what they learned at GCSE. Yeah, all very good again. And again, you could link this back to GCSE if they're coming into year 12 with the example of kilowatt hours. It's a really nice one. Or also from a real life example, sometimes having to convert imperial units, particularly if you're working with people from the United States who still use a lot more imperial units than we do. Yeah, lovely. And nice use of your graphic there on the right hand side, particularly for displacement and distance. I think that's a really good one to really remind students of coming in. One of the ways I tend to look at it now at sort of A level is I might say to them, well, you know, imagine if you start off where you're sitting right now and you do this long journey, you end up back here later on. It's almost as though the universe blinked and nothing appears to have happened. And it's quite a nice way of getting them to think about this idea of the overall result of an action. Yeah, very nice. And again, nice that you've got the drawing and the calculation in there. You tend to find that when they get to A level, a lot of students are perhaps more confident with Pythagoras, strangely, than actually drawing vectors. So when you come to teach this, I would spend a little bit of time getting the students to actually practice drawing out and finding resultant vectors on graph paper. It's a really good way of making them think about what they're learning and practicing a skill that they don't really do much of at GCSE. Yeah, again, all very good. One thing that's worth thinking about when you teach this is explaining to students why they need to resolve vectors. We quite often jump into it straight away, and students quite like it because it's, you know, trigonometry, and they generally tend to be quite good mathematicians. But I quite often start by giving them an example and imagining something where I've got a whole lot of different forces at different angles, and I'm trying to work out the overall effect. And then the idea that if I could resolve the forces, I could work out the total vertical, total horizontal. And then use that to calculate the overall effect of the force going back to resultant forces. I think just put it in context is quite important. And the sooner we can start talking about vertical and horizontal planes at A level, the better, because I think, again, that's something which they only really touch on quite basically at GCSE. Yeah, lovely example. I would just, again, perhaps put a little bit more explanation in here if I were doing this in a lesson. I think what I would probably look at is just explaining the importance of this, because obviously what we're doing is we're working out the force accelerating the block down the slope. One of the things I find a lot of students don't grasp fully, and maybe we don't always teach it as well as we could, is that when at GCSE they learn about F equals ma, we don't always make a big fuss about the fact that F is actually the resultant force. So it's the resultant force that affects the acceleration. And so I think sometimes students can sort of forget that they've got to work out the resultant force acting. So if this was a simple example here where there's no friction, then we need to know the resultant force in the direction of the acceleration. That's why we need to work out mg sine theta. If we had a slightly more complex example where we were taking into account friction, in that case, if I had friction acting in this direction, then I would also have to take that into account. So it would actually be mg sine theta minus the friction would equal ma. So I think it's just really worth re-emphasizing that every time we teach it. Okay, so this all looks fine to me. You've mentioned here that they may need to revisit logarithmic rules. I would agree with that. Most GCSE maths syllabuses don't have logs in them, so this may well be new to all of your students. And some of your students, if they're not taking A-level maths, may not get taught this until they arrive in your classroom. So it's really worth spending a bit of time on this. I put 2 links down there which I think are quite useful. One's a real simple introduction to logs, and then the second one is about natural logs. I think one of the things that the second one is good at is it makes that point that natural logs are really important in physics. And I think one of the reasons is that, as they mentioned on the video, it's partly because lots of things in physics can be sort of explained by exponential growth and decay, and other subjects for that matter. And from a mathematical point of view, what's interesting about e to the x is that when I differentiate it, in effect, the gradient of the graph is equal to x. So the differential of e to the x is actually equal to e to the x. So the gradient is equal to the value on the graph. So that's why those graphs are particularly interesting. But have a quick look at those links. You might find them useful in the future, either for teaching the students or just confirming your own knowledge. It's a bit of the physics syllabus I never really liked, and I always used to just double check myself when I hadn't taught it for a while. Yeah, great graphic and a nice sort of revision of what they should know from GCSE, but it's really good going over these terms again because students tend to forget them. Yeah, I won't talk about this in much depth because obviously I've sent you the earlier video, and I just think that from the materials perhaps that you had to look at, it's just really important to be happy about the difference between uncertainties and errors, and then how we might use those in calculating errors in an entire equation, or how we might use absolute uncertainties. It might also just be worth looking at whichever syllabus you happen to teach. Have a look and see what they are requiring you to teach and how you're requiring to teach it, because certainly with the ones that I've used in the past, we never used uncertainties in the way that was in that example you were given. Anyway, hopefully the little video clip I sent you already is helpful for that. And again, I refer to my previous video I sent you. I think this is a lovely experiment, but I probably wouldn't use it to look at uncertainties. I would probably use it to plot a graph and work out from the gradient what g is. So have a quick look at the example in my video. And again, I'll refer you to my previous video on this slide, but I suspect that your understanding of errors is perfectly fine. Yeah, this is good. Just put a couple of points here. First of all, just bear in mind if your students aren't doing Maths A-level, depending on what your school requirements are that you're at, they may not understand what the term integrate means. And I'm not sure that I would call integrating the rate of change. So on the next slide, I'm just going to put a little bit here about differentiation and integration and how that perhaps looks better in terms of kinematics. Okay, so just bearing in mind that your students may or may not be doing A-level maths. So from GCSE, what they will definitely know is they will have looked at graphs looking at distance time. Quite often it's distance time at GCSE rather than displacement time. Depending on the GCSE syllabus you take, they can be a little bit cavalier about what they say, whether they call it displacement or distance. So they'll have done things like you've mentioned, and I think in a later slide, that in this example, for example, this would be stationary, and then they'll look at graphs, for example, where they are understanding that a straight line is going to represent, oh, that's a terrible straight line, but you know what I mean. This would represent constant, in this case, constant speed, or if it's a displacement time graph, it would represent constant velocity. So what they do appreciate at GCSE is that the gradient of this graph is going to equal the speed. But what I'd like to do now is update that as they go into A level. So if I was looking at this as an A level now, what I'd really encourage my students to do now is say we're looking at displacement time and get them out of using S for speed, which is a habit they pick up at GCSE, not their fault, it's because it tends to be in a lot of the syllabuses. So now if I've got displacement time and I calculate the gradient, then the gradient is going to equal velocity. So velocity is equal to the change in displacement divided by the change in time. And I'm using the delta here for change on purpose. They do that at GCSE. And it means that the gradient is therefore the velocity. And they also learn at GCSE, particularly at the higher tier, which is that if they've got a curve, they would have to find the tangent, and the tangent would still give them the velocity. So velocity is still change in displacement over change in time. So the move forward at A level, if they're doing A level maths, is that they will then look at differentiation. And differentiation would give me that velocity is equal to ds by dt. It's the differential of displacement with respect to time. And differentiation gives us the rate of change. Because I've got time on the bottom, then it's the rate of change of displacement. So actually the definition of velocity is the rate of change of displacement. And that's why I made the comment about it saying rate on that graphic in your previous slide. So velocity is defined as the rate of change of displacement. And therefore, the gradient of a displacement time graph, because we're now trying to ignore this distance time stuff they learned at GCSE, the gradient is equal to velocity. If we then look at a velocity time graph, and again making sure that they come out of that GCSE habit of using S for speed, then in this case, if I work out the gradient, they'll have learned at GCSE that this represents constant acceleration, and that therefore the gradient of this graph is acceleration. So acceleration is equal to the change in velocity divided by the change in time. And again, they should have learned this notation at GCSE, change in velocity divided by change in time. So acceleration, when I'm looking at, when I differentiate it, is the differential of velocity with respect to time. So acceleration is defined as the rate of change of velocity. So that means, again, they'll have learned that if they have a curvy graph, they can draw a tangent to it, and it's a terrible tangent, but then again, acceleration here would be the change in velocity with respect to time. And what they're trying to understand, because I think a lot of students sort of forget what the purpose of differentiation is, but actually differentiation in both of these examples is a way of calculating the gradient at any point on that graph. So it's nice and easy on a straight line graph to work out a gradient. They've learned that at GCSE, but at GCSE they learn to do a tangent if it's a curve. And of course there's an inaccuracy in that. And so differentiation, well, the whole process was designed, if you like, by people like Newton and Leibniz. And what they were trying to do is find a very specific way of working out the exact gradient at any point on that curve. So therefore, I do take a bit of time when I'm teaching this to students to make sure they really understand that differentiation is a mathematical way of finding the exact gradient at any point on a graph, including a curve. So they really need to have this understanding that it's differentiation that takes us from the displacement time graph to the velocity time graph to the acceleration time graph. I'm just going to put a little bit more on that on the next slide. Yeah, so at the moment then what we've got is we've got in effect that if I look at it in this way, I've got my displacement time graph, I've got a velocity time graph, and then we've got an acceleration time graph. And so what we've looked at is that if I differentiate, then I'm going in this direction. So if I differentiate displacement with respect to time, I end up with velocity, and if I differentiate velocity with respect to time, I end up with acceleration. And we know that that's the gradient of the graph. The other thing to include in that, at GCSE, the students do learn that the area underneath a velocity time graph is equal to the displacement. So if I shade in an area now, if I was to work out the area underneath that graph, the area would equal the displacement. And that means that, in effect, I'm going from the velocity time graph to the displacement time graph. And finding the area is integration. So integration is finding the area underneath a graph. So in this case, I'm integrating velocity with respect to time, and I end up with displacement. What they don't learn at GCSE, which is the next sort of stage on, is that the area underneath an acceleration time graph would therefore be the velocity. So therefore area equals velocity. So the integral of acceleration with respect to time gives me velocity. So what that means is that if I go in this direction, finding the area or integrating, so this is the, oh, excuse me, let me just rub that out a second. Okay, if I integrate acceleration, okay, in this direction, and in this direction I'm integrating velocity. So just make sure you're sort of clear on that. I'm not sure that infographic was great. Yeah, this is lovely, and very much a nice review of what they should already know from GCSE. Yeah, this is lovely. Again, depending on the GCSE syllabus that the students have followed, they will all definitely know V equals U plus AT. Slightly randomly, this one seems to have crept into GCSE. I'll show you in a minute why I don't think they're the most natural two to start with. But certainly the first three, if you know the first three, actually you don't need the other two, you can derive those. But that would then hark back to what they've done at GCSE. And then on the next slide, I'm just going to show you a quick derivation, which I find useful because it brings together that manipulation of algebra and the graphs that we've looked at in the last bit there. So I'll just show you that in a second. Okay, so I find this derivation quite useful because it brings together lots of ideas that we've already learned. So we know from the previous slide that the definition of acceleration is the change in velocity with respect to time. And of course, we know that change in velocity is v minus u, the final velocity, take away the initial velocity divided by t, and therefore the equation v equals u plus at, rearranging that, is actually just the definition of acceleration. So it's sort of an empirical equation, if you like. But what we've also looked at is that if we've got a velocity time graph and I've got something which is accelerating at a constant rate, as you've rightly said, those equations are only true where I've got constant acceleration. It'd have to be a straight line graph. Let's say it's starting at initial velocity of u, and over here it's going to finish at a velocity of v. It's going to take time t. Then what we know is that the area under a velocity time graph, which we've just looked at, if I look at the area under here, that's going to equal the displacement. So the area is equal to S, the displacement. So if I now have a look at the equation we've got there, we know area is equal to S. I'm now going to split this into two bits. So I've got the area of this rectangle down here. Okay. And the area of that rectangle is going to be U multiplied by T. And then I've got to add on to that the area of this triangle here. And we know that the area of a triangle is a half base times height. So I've got a half. The side there is V minus U. That's this bit here, between here and here. And the base is equal to T. So that's given me an equation, S equals UT plus half V minus U multiplied by T. Now, if I go back to my original equation up here, V equals U plus AT, up here, then I know that V minus U, which is what's in this bracket here, is equal to AT. So I'm going to pop that into the equation. S equals UT plus a half, and now we've got AT multiplied by t. That gives us s equals ut plus a half at squared. So it's just a really nice example of how you can use their existing knowledge about graphs and the definition of acceleration to derive this second equation. And if you love doing algebra, you can find derivations for the other equations as well. But I just like that one. It's just a really nice way of bringing lots of information together. Okay, so just have a little look at this because I think you've got two different things going on here. So if I look at up here, first of all is that I would just make sure if I'm doing this, I'm explaining that if ut has gone from this equation, it's got to be because u is equal to 0. Which is fine, but that's not the case in the example you've shown over here on the right. So this would work if the ball bearing was being timed for when it was dropped here, where u is equal to 0, until the time when it hits the ground. So in that case, the time it took for the ball bearing to fall will give me t. And if I know how far it's fallen, then I can work out g. But you've got to assume that u is equal to 0 if you're using this equation. So just watch out for that, because in this example here on this side, I've got a distance h, or if you like, displacement. I'm going to have an initial velocity here, which won't be 0, and I've got a final velocity here, which will be v. So I really ought to be using v squared equals u squared plus 2as. In which case v squared minus u squared divided by 2s would give me the acceleration, or g, and of course s in effect is h here, and then those two light gates should give you v squared and u squared, or v and u. So just be a bit careful here about mixing up those two experiments, because in this case over here u wouldn't be 0. Yeah, this is fine. This is a little bit like the example I gave in the previous video I sent you. I would just be aware to make sure that you explain where this comes from, because it's probably not obvious to students, particularly when you put in the h as opposed to the s in there. So I would rearrange that s equals ut plus half at squared and explain where this comes from. And then this box here is really useful to explain that it relates to y equals mx plus c from GCSE. Yeah, this is nice. One of the things that used to be at the old AS level, where there was always a question on this in the AS paper, and they're increasingly putting them into the GCSE higher tier papers now. What students are really poor at doing is they're quite happy to say, you know, there's just weight acting at the start, so the forces are unbalanced, therefore the object accelerates. And when I'm doing this, I'd really relate back to Newton's first law, this idea that things accelerate when there's a net force acting on them, and that therefore it starts off accelerating. What they're terrible at is remembering to say that as the object speeds up, the drag increases, and that idea that increasing drag occurs as a result of increasing velocity. So that's something to just double check they've already got. And then this idea again that the forces are balanced at the point at which then terminal velocity is reached, because now at terminal velocity it's going at a constant velocity downwards. So it's really worth just recapping that from GCSE. Yeah, again, nice and nice showing of the velocity time graph. Worth, again, just spending a couple of minutes reminding them of this idea that when we're looking at the graph here, we've got what initially looks like a constant acceleration, but as the gradient is getting less steep, that suggests the acceleration is getting less. And from F equals ma, we know that if the acceleration is decreasing, then the net force must therefore be decreasing. Okay, until we get to the point where, at this point where it's flat, then if acceleration is 0, the net force must be 0. So it's really nice just going back, relating Newton's laws to those graphs and just pulling together all those things that they learned at GCSE. They almost certainly won't have looked at this particular kind of graph at GCSE. Yeah, this is fine. I think you probably want to draw this out in a little bit more depth if you're teaching it, because there's a lot of information on here very quickly. And so I tend to split this into, a simple projectile and then a more complex projectile. So have a quick look at the next couple of slides and see if you find those useful. Okay, so I hope you find this a little bit useful. When I teach projectiles, I tend to start with a really simple example. So for example, I kick a football off of a cliff and I give it a horizontal velocity of u, and the cliff is going to be a height h. Okay, so now we're going to consider this in the horizontal and vertical directions, and that's why I think I mentioned earlier on that the more fuss we make about thinking about everything in horizontal or vertical directions at A level, the better. We are preparing them in effect for undergraduate studies where they'll add in Z, the third direction, and they have to start thinking about things moving in 3 directions. So it's really good practice. So in this direction, I've got a value of ux, which is the whichever velocity I kick the ball with. In this direction, uy is going to equal 0 because I haven't given it any downward velocity. Okay, so that's the first thing there. We know that it's going to fall a distance h. So if I look at the y direction first, then I've got the u in the y direction is 0. I know that the acceleration is going to equal g, and I know that it's going to travel, the displacement will be a height of h. If I use the equation s equals ut plus a half at squared, then we know this is going to disappear because u is 0, which leaves me with h is equal to a half gt squared. And if I rearrange that, I've got 2h divided by g and then square root all that, and that gives me time. So that's how much time the projectile is going to spend in the air. If I then look at the x direction, then ux is just whatever it is that we've chosen as a velocity. We know the acceleration is 0. I've just kicked it. There's no forces acting on that ball in the horizontal direction once I've kicked it. So there's no net force. So the acceleration is 0. We are completely ignoring air resistance because it makes life a bit awkward at A level. And then we know that the time spent in the air is going to be root 2h upon g, because once it hits the ground, we then consider it to have stopped. So now if I want to work out how far it's travelled, or its range, if you like, we quite often refer to it as range, which is the displacement, is going to equal, now it's just going to be u times t. We are just going back to the old equation that velocity is equal to displacement divided by time. Okay, there's no acceleration here. So it's not just constant like the Suvat equations, there's no acceleration at that point. Speed just equals distance divided by time. So if I now put this into the equation, then the range is going to equal ux, which is the velocity we kick the ball with, multiplied by the root of 2h upon g. So those are all the equations that I can use for understanding what happens to that particular ball. So in this example, we can now work out what the time is it takes to travel. I can work out how far it travels. Okay, so if I look at the example now that was on your slide there, then what we tend to think about is the fact we've got some kind of projectile which has been shot off at a velocity of v at an angle of theta to the horizontal. And the first thing I can do, which you've shown in your slide, is we can define the initial velocity in the x direction as equaling v cos theta, and the initial velocity in the y direction is now v sine theta. If I now look at the x and y directions separately, I'm going to start with the y direction again. So in the y direction, I know that the initial velocity is going to equal v sine theta. I know that the acceleration, we put it as negative g now because it's going upwards, and therefore the force due to gravity is slowing it down. So we've got a negative value for g. And then the thing that I think students find hardest is that the overall displacement is going to be 0, because if we think about our projectile going up and down again, then in the vertical direction, it hasn't gone anywhere. It's gone up and down again. The displacement is 0. That's the bit that students need to get their heads around. So now we come back to our equation, s equals ut plus a half at squared, and I start putting those values in. So we know that s is 0. We know that u is now v sine theta, and I've got to multiply that by t, so I'm going to put t in here because it's a little bit neater. We've got to do a minus sign now. We've got a half gt squared. So now I can make vt sine theta equal to a half gt squared, and I can now cancel the t's. So I've now got v sine theta on this side, and if I rearrange, I'm going to put 2 from the half, and I'm going to divide by g, and that now, oh, sorry about the messy bit there, it's going to equal t. So I've now got an expression for the time that the projectile spends in the air, which is exactly the same as what I did in the previous slide for finding the time in the air. We use the y direction. I'm just going to swap colours to make it a little bit clearer. I'm now going to look at the x direction, and again we now know that the initial velocity in the x direction is v cos theta. It's still not accelerating in this direction. Okay, it's not given any net force in that direction, so the acceleration is still 0, and that means that once again I can go back to my really simple equation of in effect velocity or speed is equal distance or displacement divided by time, because there is no acceleration. So now if I want to find the range or the displacement in the horizontal direction, that's going to equal u times t, and of course we're in the x direction, so s is now going to equal ux, which is v cos theta, multiplied by this whole big expression here for t. So we've now got 2v sine theta divided by, oh, across there, g. And then I can simplify that a little bit, not very simple, but there we go. 2v squared, 2 v's, sine theta cos theta divided by g. Oh, yeah. Okay. So now what we've got an expression for how long it's in the air, and we've got an expression for the range. Because we know the time in the air, one thing that we can do quite simply is we can get rid of this. To find out the time to get to maximum height, it's going to be halfway along. So the time to maximum height will just be v sine theta divided by g. Now I've got a time and I know the initial velocity, I can now work out the maximum height. Okay, so hopefully you find that a little bit useful. Yeah, I think what you're using is perfectly fine. Certainly IOP I find really useful. I've stuck a couple at the bottom there. PhET simulations I really like for teaching and getting kids to use. I've put out physics online. It's really difficult finding high quality physics A-level revision stuff online. There's loads of really good stuff for biology and chemistry. Maybe there's a market for it, but I find those quite useful. See what you think. Yeah, well done on going up from 75.5% to 90%. That's really great. And yeah, I think the problem with coming back to mechanics after a long time is the sort of basic understanding. I think it's there. It's trying to get to understand all those different kinds of examples. So don't worry, we all do that, and it will come with experience. And hopefully, wherever you end up training and teaching, there'll be other colleagues with you that can help you out whenever you get new different examples crop up. Yeah, I think they're probably quite common. The projectiles, have a look at those 2 slides I put in and see if they're of help. If not, give me a shout and I can always provide something else for you. And the uncertainties, I'm hoping that the previous video I sent you has given you a few ideas on that. I just think the materials are perhaps a little bit confusing. Free body diagrams, less sure what you're stuck on. So if you've got any particular examples where you think that you struggle to get it right and you'd like some advice, just ping me an example and I can always come back to you with some ideas. And yeah, again, I would say don't worry too much about the EV versus V until you've done the electronics module. I'm not sure, I don't know if that came out of the examples given to you in the VidLearn unit, but I'm not sure that's a great example in a mechanics module. So I'd come back to that later when you've had a chance to revise what electron volts are. I think thinking about things like kilowatt hours or converting from imperial to metric measures is a much better example for this module. And it's great, I think, that you found these particular things easier. These are definitely things that students learn at GCSE. So if you're feeling confident about those, then certainly teaching the GCSE course should mean that you feel very confident and that you've got all the right foundations to build on. Okay, I'm going to tackle the number 11 first. So not sure that they've not got something a bit wrong here. So if I was going to rearrange this, the first thing I would do is do n divided by n naught is equal to e to the minus lambda t. And then I would take natural logs on both sides. So that then leaves me with the natural log on the left-hand side of n divided by n naught is equal to, and because by taking natural logs and getting rid of the e in effect, I end up with minus lambda t. So to get lambda on its own, I'm going to divide by minus t. That's the bit which is a bit odd. So when I do that, I end up with minus 1 divided by t on the left-hand side, multiplied by the natural log of n over n naught is equal to lambda. So I've now got lambda on its own successfully here. Now, the negative log means I can now put 1 upon t natural log of n naught divided by n equals lambda. This is why it's really worth going back and look at your logs, because I always have to think back hard about this. Where I'm not sure about their answer is when I have a natural log of something divided by something else, it becomes a negative. So what I should have is log n naught minus log of n divided by t equals lambda. Generally speaking, whenever we actually use this in context, because I mean you'll see this in the radiation topic, we tend to stick at this stage and we actually work out this fraction. So for example, if I've started with 100 nuclei and I've now got 50, then this is a fraction, and that's a much more useful way of looking at it rather than doing the log then taking away another log. So I think that's what 11 is supposed to say. I think 20 is okay. I've tried having a look at 14 and 15 of this whole idea about these absolute uncertainties and absolute percentage uncertainties, and I can't work out where they've got those from either. What I'm going to do in the next slide is I'll pop a link I've found to something else that explains this in terms of uncertainties, which I find quite useful. I'm not sure it quite matches up with what's on here. But again, when you come to teaching this at A level, look at your syllabus and what they want you to do and how they want you to lay things out, because it seems to me that in some syllabuses, how they discuss errors and uncertainties gets a little bit muddled. So I'll put that link in the next slide and hopefully that'll be a bit useful. Okay, so I've just stuck this link in, and what I'll do is I'll send you an email with the links from the presentation in so you can access them more easily. See if this makes more sense to you. As I say, looking at what they've put in the VidLearn materials, I think what they've done on uncertainties and errors and absolute uncertainties and percentages is a little bit muddling. This might make a bit more sense to you, but I think look at your particular syllabus when you come to teach and see what you think. Anyway, hopefully the sort of verbal notes have been useful. Sorry if I get a bit rambling, but sometimes I find it easier than trying to write it down in a Word document and send it on. Any questions, or just ping me an email. Okay, well done on passing this one, and good luck for the next one.